In this video, we are going to discuss physical properties of alkenes as well as reactions of alkenes. So the physical properties of alkenes are really similar to alkanes. Alkenes are nonpolar. So remember, alkenes consist of hydrogens and carbons. So if you have, for instance, this alkene, the carbon-hydrogen bonds are relatively nonpolar, and the carbon-carbon bonds are nonpolar. So we should also only see really weak intermolecular forces between alkenes. Now, because these alkenes are nonpolar, they're also insoluble in water. So they don't dissolve in water, and they're actually going to separate into their own layer. These alkenes are soluble in nonpolar solvents. So some nonpolar solvents we might use would be, for instance, hexane. So hexane has 6 carbons. That's a pretty common nonpolar solvent. Now, alkenes are also typically less dense than water. So remember, the density of water is 1 gram per milliliter. So the density of an alkene would be less than that, so maybe 0.9 or 0.8, or even less. Additionally, alkenes have an unpleasant gasoline-like odor. So that's one way that you can sort of narrow down whether you have an alkene or not. They don't smell particularly great. Another thing to keep in mind is that similar to alkanes, if you keep adding carbons and hydrogens onto the chain of carbons, the boiling point is going to increase, and the melting point will also increase. So, for example, let's look at ethene, which is just 2 carbons, 4 hydrogens, and then we have a double bond between the 2 carbons. Notice that its boiling point is negative 104 degrees Celsius. Its melting point is negative 169 degrees Celsius. Now, as we go down this chart, we're adding more carbons and hydrogens onto that molecule. So we're creating propene, and then 1 butene, 1 pentene, 1 hexene, etc. And notice that the boiling points are less negative as we go down, so they're increasing. And the melting points are also increasing, although there's a little discrepancy here. Their melting points are pretty similar. And then the density is also increasing with an increasing number of carbons and hydrogens in the alkene. Now let's move on to alkene reactions. So alkenes are very reactive. And if we think about alkanes, we said that alkanes are not very reactive. There's only a couple of reactions that they can do. But alkenes have more reactions that they can perform, and that's due to their double bond. So let's look at kind of the general reaction that an alkene can go through. So we've got our double bond, and we're just going to add A and B across the double bond. So what we're doing is we're breaking the pi bond, so that double bond, and then we're going to create 2 new bonds, one with A and one with B. So A goes on 1 carbon, B goes on the other carbon. They don't add to the same carbon. And that makes sense if we think about the electrons. So let's look at the electrons in this top bond here. So what we're really doing is breaking that bond, and then we're also going to break the bond between A and B. And then our red electrons are going to create new covalent bonds with the blue electrons from A and B. Now these reactions are called addition reactions because we're adding something across that double bond. Now there's plenty of reactions we can perform. These are the four main ones we're going to focus on. So if we look at our starting point, the alkene, we can do four different reactions. So we could add Br2 or Cl2 across a double bond, and that's going to give us something called a haloalkane. So we're going to add 2 bromines or 2 chlorines across the double bond. We could also add 2 hydrogen atoms across the double bond, and that's going to take a double bond and turn it into a single bond. So we'll end up with an alkane. Now notice we have this extra atom here, platinum. So this just acts as a catalyst that helps the reaction along. Unfortunately, we can't just add hydrogen to a double bond. We need something to kind of give it a boost and help it along. And so platinum is typically used as the catalyst here. All right, now what if we add hydrobromic acid or hydrochloric acid? Well, we'll also end up with something called a haloalkane, but we're only going to add 1 bromine or 1 chlorine, and then the other side will get a hydrogen. So we'll talk more about that in a bit. Now these products you can also call alkyl halides. So you might see that name too. The last reaction here, we could add water across the double bond. Now, in order for this reaction to work, we need an acid, or at least a stronger acid than water. So we're going to use sulfuric acid, H2SO4. So again, this just helps the reaction occur. At the end of this reaction, we're going to end up with an alcohol. So we'll get an OH group. Now remember, if you haven't gone through those functional group cards yet, I have some flashcards on those different functional groups like alcohols and alkenes, etc. So make sure to go through those. All right, so let's look at each of these reactions in a little more detail. So in the first reaction, we're going to focus on halogenation. So halogenation, which is an addition reaction, produces what are called haloalkanes or alkyl halides. So again, we start with our double bond, and we're going to break the double bond, leaving the single bond. We're also going to break this bond between the 2 bromine atoms. And then we're going to form 2 new bonds. So one carbon gets 1 bromine, the other carbon gets the other bromine. So again, those bromine atoms are going to add to separate carbons. They're not going to add to the same one. Now we call this halogenation because bromine is a halogen. You could also use chlorine. So you could also add Cl2 across the double bond. All right. So that's not too bad, right? Now the next reaction is hydrogenation. So hydrogenation, if you want to think of it that way. So hydrogenation reactions can occur in the presence of a catalyst. So earlier we said platinum is typically used, but you could also use the element called palladium, Pd, or nickel. Any of those will work. So again, we're going to break our double bond, and we're also going to break the bond between these hydrogen atoms. And then we're going to create two new bonds with those hydrogen atoms. Now, you might be wondering, how can we add a gas across a double bond? Because hydrogen, H2, is a gas, right? So that's why we need this catalyst. So what's really interesting is we have our catalyst, so a metal surface, and then the hydrogen atoms stick to the surface, and then the alkene kind of comes in and creates new bonds with those hydrogen atoms. So we kind of trap the gas on the surface there, and then the alkene comes in and creates new bonds. So this would be our platinum surface. So you might have heard of hydrogenation before. For instance, the hydrogenation of vegetable oils is an important commercial process, and that produces products like margarine and shortening, which you might use in baking or other types of cooking. Now, there are something called polyunsaturated molecules, and those will contain several double bonds that you could then add hydrogen to. So poly means that there's multiple or many of something, and then unsaturated tells us that we don't have as many hydrogens as we could have, and that's due to those double bonds. So hydrogenation of polyunsaturated molecules, interestingly enough, raises the melting points of the molecules. So that can be really important in things like cooking. But because you're adding more hydrogens onto your molecule through hydrogenation, that's going to require more energy in order to melt. So all of these things go back to chemistry and energy. All right, now we're going to go on to the next type of reaction, but before we do, we have to talk about something called Markovnikov's rule. So this is named after a Russian chemist, and he did experiments on unsymmetrical alkenes, or asymmetrical alkenes. And his question was, okay, if I have a double bond and I want to add, let's say, hydrobromic acid, so HX, where the X is either bromine or chlorine, then what's going to add to what? Where does the hydrogen go? Where does the halogen go? Because you could end up with multiple products. So for instance, looking down below, we have an unsymmetrical alkene. So one side has two hydrogens, the other side has a hydrogen and a methyl group, right? So this double bond is unsymmetrical, and we can even draw it out just to kind of show that it is in fact unsymmetrical. So if we're going to add, let's say, HBr across the double bond, what side does the hydrogen go on and what side does the bromine go on? How do we know where it goes? Well, what Markovnikov found was that the hydrogen predominantly attaches to the carbon that's already bonded to the most hydrogens. Or you can think of this as the rich get richer, which is pretty relevant right now. So our hydrogen is going to add to the side that has more hydrogens. So in this alkene, that would be the left side. So it's going to attach to the left side. Bromine is going to attach to the side with less hydrogens. So that would be the other carbon in the double bond. Okay. So let's look at the addition of hydrobromic or hydrochloric acid to double bonds. Now, sometimes we don't have to worry about Markovnikov's rule. So if you do have a symmetrical alkene, you don't have to worry about it because you're going to end up with the same product no matter which side these atoms add to. So for example, let's say we have just a generic alkene here. We're going to break that double bond like usual. We're also going to break the bond between hydrogen and chlorine. And then we create two new bonds, one with hydrogen, one with chlorine. And again, it doesn't really matter which side the chlorine adds to in this case because we'll still get the same molecule. It'll just be a mirror image, or we could just flip it like a pancake and get the same picture. Additionally, down below that, we have another symmetrical alkene. So on the left-hand side, that carbon is bonded to a hydrogen and a methyl group. On the other side, that carbon is also bonded to a hydrogen and a methyl group. So again, it doesn't really matter which side the hydrogen adds to because both carbons have the same number of hydrogens attached. However, when we look at the very last example on the bottom, again, we have that asymmetrical or unsymmetrical alkene. So when we break the double bond and we break the bond between hydrogen and bromine, there's two possible outcomes. Either the hydrogen adds to the side with less hydrogens. So let's just highlight that. Or the side with more hydrogens. But what Markovnikov found, again, is that the major product was the one where hydrogen attaches to the side with more hydrogens. So we can see that in the answer that's boxed in red here. And then bromine is attached to the side with less hydrogens. So that is the major product. So you might see a very, very tiny amount of the other product where hydrogen did add to the side with less hydrogens, but it's so minor that we're just not even going to worry about it. And we're just going to focus on the major product where the hydrogen adds to the side with more hydrogens. All right, so let's do some practice problems. Let's go over some of these reactions. Okay, so I'm going to write out a few reactions, and I want you to either figure out the product or the reactant. Okay, so let's draw a few reactions here. Oh, platinum. Okay, so I want you to draw the product of that reaction. And then in the next example, I also want you to figure out the product. In the last example, I want you to work backwards and figure out what starting material do you need in order for the reaction to work. Because sometimes in chemistry we want to produce a specific product, so we have to figure out what our starting materials should be. All right, so pause the video, see if you can figure out these different products and reactants, and when you're done, you can unpause and we'll go over them together. Okay, so let's start with the first one at the top. So you can see that I drew the red electrons for the double bond and the blue electrons for our hydrogens. So we're going to break those bonds and we're going to form two new bonds. See if I can squeeze this in here. All right, so now we've got our two new bonds. Now you could draw the hydrogens up above if you want to keep track of where they went, or we know that those two carbons on the double bond are each gaining a hydrogen, so we could write that as CH2 and CH2 because they each gained a hydrogen. So you could also write it that way. Okay, let's look at the second problem. So again, we have an unsymmetrical alkene and we're adding hydrobromic acid, HBr. So does it matter which side the hydrogen adds to? Yes. Okay, so we need to figure out which side has more hydrogens. That's the side the hydrogen will add to. Okay, so let's look on the left-hand side. How many hydrogens are there on the left-hand carbon? Just one. What about the right-hand carbon? Two. Okay, so which one has more hydrogens? The right-hand carbon, the green one. Okay, so that's the side that the hydrogen will add to, according to Markovnikov's rule. All right, so let's break our double bond. All right, and then we're also going to break our single bond between hydrogen and bromine, and we're adding hydrogen to the side with more hydrogens, and we're adding bromine to the side with less hydrogens. Now, again, because we're adding hydrogen to that last carbon, we don't necessarily have to draw it up above. We could just change the number 2 to 3 to indicate that a hydrogen was added on that side. Okay, last question. Let's see, so we don't know what our starting material is, but we do know that we're adding 2 bromines across the double bond. Now, looking at our product and where those bromines added, where was the double bond? Probably between these 2 carbons in the middle, right? Because that's where the bromines ended up. So what we'll do is we'll kind of work backwards and we'll say, okay, we had a chain of 4 carbons and there must have been a double bond between those 2 middle carbons. And if you're not quite sure if that's right, you could always work forwards and see where the bromines would add to figure out if you got the right answer. Okay, so next, let's talk about hydration. So in a hydration reaction, we're adding water across a double bond. So that might sound a little strange, right? How do we add water across a double bond? Well, what we're really doing is, again, we're breaking our double bond, and then we're going to break the bond between one of the hydrogens on water and oxygen. So then when we form our 2 new bonds, hydrogen will add to one side and OH will add to the other side. So that's why we end up forming an alcohol, because we have this OH group bonded to one of the carbons now. Now again, you do need sulfuric acid to help this reaction along. So just remember that you always need that acid there. Okay, so looking down below that, we have 2-butene. So this is a symmetrical alkene, so it doesn't really matter which side the hydrogen adds to. But look below that at propene. This is an unsymmetrical alkene, so now we have to use Markovnikov's rule and figure out which side the hydrogen will add to. So there's a couple possibilities. The hydrogen could either add to the carbon with less hydrogens or the carbon with more hydrogens. But the major product is the one where hydrogen adds to the more substituted, or sorry, the carbon with more hydrogens. And then the OH group adds to the side with less hydrogens. Now again, we will end up with a very, very tiny amount of the other product where hydrogen adds to the side with less hydrogens, but we kind of tend to ignore the minor product and we just focus on our major product. Okay, so let's do a practice problem or two for hydration reactions. Okay, so let's say we have the following. All right, so for the first one, I want you to figure out what your product would be, and you can just focus on the major product. For the second reaction, I want you to figure out what your starting material would be. We always need our acid catalyst. Okay, so pause the video, see if you can figure out these two problems, and when you unpause, we'll go over them together. All right, let's start with the first problem on the top. So we have an unsymmetrical alkene. So does it matter which side the hydrogen adds to? Yes. Okay, so we want to find the side that has more hydrogen. So would that be the left-hand side or the right-hand side? The right-hand side. Okay, so we know hydrogen will add to the right. So let's draw this out. So that means that the OH group will add to the left-hand side. Now again, you could just change that 2 into a 3 on the last carbon there to indicate that the hydrogen added to the carbon on the right. All right, let's look at our second problem. Now, if you got a little confused on this one, don't worry, I meant it to be a little more challenging. Now, there's two possibilities here, right? So, the first possibility is that the hydrogen added to this carbon here, and then the OH group obviously added to that carbon. Or the other possibility is that the hydrogen added to the carbon on the right, just like above, right? So the double bond could have been in the middle or on the end. Okay, so first possibility. We could use a symmetrical alkene, like this one. The second possibility, we could have used the same reaction we saw above. And both of these would give us the same product. So again, we want the OH group to add to the third carbon in the chain. And then it just depends on where the double bond is from there. One thing to keep in mind is remember that if you have an unsymmetrical alkene, you do end up with a very tiny amount of that other product, the minor product. So usually if we want the OH group to end up in a particular place, ideally we want to start with a symmetrical alkene if we can. So just notice that the first possibility is symmetrical. The second one is unsymmetrical or asymmetrical. All right. So that's all we'll cover in today's video. In the next video, we're going to go over aromatic compounds. In particular, we're going to focus on an aromatic compound called benzene. So I will see you then.